Thank you for the introduction. My name is Ongun Berk Kazanci, and I'm an assistant professor at the Technical University of Denmark, International Center for Indoor Environment and Energy. And today I'm going to provide an overview of resilient cooling technologies, but actually we'll focus more on two more specific systems, as there are many technologies, and within a 20-minute presentation, it's hard to talk about all of them. So just a moment to fix my laser pointer. Perfect. So I'll just very briefly talk about Subtask B of Annex 80, which a colleague from Aalborg University and myself, we are leading this Subtask B. Then I'll talk about radiant cooling systems. Then I'll talk about personalized environmental control systems. Then I'll present some results from some preliminary simulations that we've recently carried out. And then I'll briefly summarize and identify our next steps. So Subtask B is focusing on solutions, and as Philip mentioned earlier, there's Subtask A, which focuses on definitions and fundamentals. There's Subtask B, which is focusing on solutions. There's Subtask C, which is focusing on case studies, and Subtask D is basically gathering all this information and turning it into policy recommendations. So we have three main goals within the Subtask B. The first one is to develop criteria and methodology to both quantitatively and qualitatively evaluate the resiliency of existing cooling technologies. The second goal is to assess benefits, limitations, and performance of cooling technologies, but with a focus on heat waves and power outages. And then the third goal is to develop guidelines for design and implementation of resilient cooling technologies and their combinations. So as it was mentioned earlier, the annex, we divided these cooling or these solutions into four main groups. So the first one is technologies to reduce heat gains to indoor environments and to people. So for example, advanced solar shading or improved glazing can be a technology. Then the second group is to remove sensible heat from indoor environments, which could be, for example, high temperature cooling systems such as radiant cooling, which we will talk about. The third group is to enhance personal comfort apart from space cooling, which is, for example, personalized environmental control systems, which we will again talk about. And then the last group is to remove or ways to remove latent heat from indoor environments, for example, desiccant dehumidification. So our subtask, we've had two major outputs so far. Excuse me. The first one is a review paper. Here you see on the left that had the title "Resilient Cooling Strategies: A Critical Review and Qualitative Assessment." So in this review paper, we basically reviewed all the technologies that we work on within the annex, and also defined qualitative assessment methodologies and evaluated these technologies according to the qualitative assessment methodologies that we define. And then the second main output so far has been to develop dynamic simulation guidelines so that we can test the performance of resilient cooling strategies, basically to create a uniform, let's say, platform. When we do the simulations, we agree on the boundary conditions, so we can compare and get the outputs and compare them on a more even basis, regardless of who's running the simulations. And then currently what we are working on and to basically develop is to develop quantitative key performance indicators, and then more towards the end of the project to develop technology profile sheets for these technologies that we work with. So this was a very brief introduction to main items of the Subtask B work. So now I'll move on to radiant heating and cooling systems, and I'll briefly talk about what they are and what they can do. So these systems, they work with low temperature heating and high temperature cooling principle, meaning that usually water or heat transfer medium operates at temperatures that are close to the room temperatures. And by definition, for a system to be called, in this case, radiant, the heat emission and removal needs to be at least at least by half of it needs to be radiation. And depending on which surface is being used, then it's a combination of radiation and convection, and their percentages vary. As I said, they're mostly water-based, and they use floor, wall, and ceiling surfaces, so they have very large heat surface or heat transfer areas. And this is also the main reason that allows why this low temperature heating and high temperature cooling principle can be realized. There are three main types. The first type is radiant heating and cooling panels, which are usually suspended from ceilings, and they are detached from the building structure. The second type is also known as radiant surface systems, and these are pipes that are embedded in the building structure, but they are isolated from the main building structure. And then the third type is what's commonly known as thermally active building systems, which are pipes that are embedded in the main building structure, so we can activate and control the thermal behavior of the building or of the surfaces in the building. So they look like this. Usually, this is a typical view of radiant ceiling panels. As I said, they're usually suspended from the ceilings. And then here we have floor, wall, and ceiling systems. As I said, they're embedded in the surfaces, but they're usually isolated or insulated from the actual building structure. And then the last one is the thermoactive building systems, where we have the pipes, here you could see, embedded in the main structure of the building, and usually used in multi-story buildings. So they have several benefits. I have listed them here, but due to time concerns, I will not go into the details, because we'll revisit some of them later in the presentation. But basically, they have several benefits in terms of energy performance, indoor environmental quality, and also system operation compared to more conventional systems such as mechanical air conditioning. After this brief introduction to radiant systems, now I'll move on to personalized environmental control systems. As its name suggests, these systems, they try to create a personalized space around the occupant. Even though we use this terminology now, personalized microenvironmental control systems, you could see them differently or being referred to differently in certain contexts, such as microclimatization systems, localized heating and cooling systems, or personalized ventilation, and so forth. Here, when we say a personalized environmental control system, PECS, I'll refer to it as in the rest of the presentation. Here we talk about that they should be able to heat, they should be able to cool, they should be able to ventilate, which is with fresh air or clean air. They should be able to have the lighting and also acoustic functions. So something that's addressing the entire indoor environmental quality spectrum. Then, as I said, they intend to condition the immediate surroundings of the occupants and not so much the entire space that it's located in. So it creates a personalized space. And one of the main benefits is that it allows these type of, let's say, temperature, air movement, or other type of indoor environmental quality factors to be adjusted based on the person's preferences. So it provides personalized control. Some examples, for example, here on the left, on the left and in the middle, we see a mixing ventilation, displacement ventilation. These two are trying to condition an entire space, while on the right-hand side, we see a personalized ventilation, which provides the fresh air, and ideally it should not get mixed with the surrounding room air, so the people get fresh air in their breathing zone. Some examples have also been combining heating, cooling, and ventilation. Here on the left, for example, we have combinations of a heated chair, of a floor heating system, or an under-desk heating panel combined with personalized ventilation. And here on the right-hand side, we have, for example, a foot warmer. We have a heated keyboard, and then also increased air movement from these type of diffusers next to the people. So again, these systems, they also have several benefits compared to total volume conditioning systems, such as they could improve comfort, health, and productivity of the occupants. People have been shown to have a higher satisfaction with the indoor environment, mainly due to two reasons. The first one being the improvements in the actual immediate indoor environment that is experienced by the occupants. So, for example, temperatures could be more comfortable, or air movement could be more comfortable. And also because of this personalized control effect, both physically and also psychologically, that people actually have control over their surroundings. When they're implemented right, there's potential for energy and cost savings as well. Both like in the research world, but also outside of the research world, there's an increasing focus on individual differences and preferences between people. Since PECS is a personalized system, it can help address these individual differences, which we'll talk about again. There's certain resiliency benefits, both in the thermal side, but also on the air quality side. And since we've just been through a pandemic and still going through, it could also help pandemic proofs on some of our buildings by minimizing the risk of cross-contamination or spread of these viruses. So after these two, let's say, brief summaries, here I tried to collect some of the benefits of radiant cooling and PECS in relation to resiliency. So we'll start with radiant cooling. So radiant cooling systems, in here I'm referring more to TAPS, the thermally active building systems. So by activating the thermal mass, it provides the possibility to absorb the heat gains over a longer period, meaning that the building thermal mass can absorb more heat because it's pre-cooled prior to the occupancy. It can allow integration of renewable energy resources. For example, if it can be coupled to a ground heat exchanger that would be affected by extreme outdoor conditions less than, for example, an air source heat pump or a chiller. They allow, since they spread the cooling load over a certain period of time, they allow peak shaving and peak shifting. So, for example, it can help the grid by not having to cool exactly at the moment when there's a cooling demand. And again, it could also help the grid by having the possibility of intermittent operation, which means that pumps can run for a while and then stop and so forth. Then when we look at the personalized environmental control systems, PECS, as I mentioned, they create a personalized space. So due to this, many studies have shown that this allows temperature set point relaxation in the ambient system, meaning that since people are, for example, at their workstations and they have personalized heating and cooling systems, the rest of the room does not need to be conditioned to, for example, 26 degrees or 27 degrees in the cooling season, but they can be conditioned to higher temperatures. And similar in the heating season as well, which is especially relevant now with what's going on in terms of energy. And both because of since people have this personalized space and of the control, higher room temperatures are acceptable. People are more accepting of this. And one of the main topics is that since this is a more personalized space, these personalized spaces can be occupied for a longer period, for example, during the heat wave, and they can also be again occupied sooner after the heat wave is over or after the power is back. So the simulation study we did tried to look into or tried to identify and quantify some of these claims that I just talked about. Of course, it's not possible to do all of it in a preliminary study, so we identified some of them, and I'll present those in the last 5-6 minutes. So we did a simulation study, a dynamic building simulation of a radiant versus a convective system or an all-air system. We basically used this office module as a case study. There's a 2-person's office room facing west and the 2-person's office room facing east, with a corridor in between. And we chose TAPS and packaged terminal air conditioner, a PTAC system. It's a convective system, as the two systems to be compared. And for tabs, we had the intermittent operation, so a 12-hour operation when the building is not occupied, and a 24-hour operation. We looked into future weather files, but we used it for Copenhagen. These are weather files developed as a part of Annex 80 work. And then we looked at lightweight and heavyweight construction, and we looked at the cases, let's say, cases with and without power outage during a heat wave. And I will not go into all of the details, but if you would like to read more about this study, you could find the details as a part of this Klima 2022 conference paper. So now I'll show the operative temperature before, during, and after a heat wave and a power outage. So here, what we have is on the y-axis, we have the operative temperature, and on the x-axis, we have the time of the year. So it starts from about July 5th and ends about mid-August. And this gray area here, or the gray zone, is where you have the heat wave and the power outage. So it starts about July 12th and runs almost until the beginning of August. And here, this is just to show you a trend of how the temperatures evolve with tab systems, both heavyweight and lightweight, and with the convective system. But in the next two slides, we have more detailed, let's say, pictures of it. So we look at first the performance of these systems in maintaining comfort conditions. So if we look at the first week of when there's the heat wave and the power outage, the structure is the same. The y-axis is the operative temperature, and the x-axis is the first week where there's a heat wave and power outage. We could see here, especially in the first 2 or 3 days, that the tabs is better at keeping the temperatures within here what we call the comfort zone. And then these 3 lines that you see here is the first one is 26 degrees Celsius, the second one is 27, and then the third line is the 28 degrees Celsius. And these correspond to the upper limits of category 2, 3, and 4, respectively, of European standard 16791 and also ISO 17771 from 2017 correspond to these categories. So here we could see in the first 2 or 3 days is that the tabs is better at keeping the temperatures within these limits. And then here on the graph on the right hand side, we could actually see how many hours the different systems can keep the temperatures below 26, 27, and 28. So we see here the best performance, and in this case, the best performance means the highest number of hours, keeping the temperatures within these ranges that we want for tabs and in the heavyweight building. And in this case, there's not a big difference between if it's intermittently operating or if it's operating constantly. So we might as well, in this case, choose to operate it intermittently. And again, here the tabs is performing better than the convective system. While in the convective system, there's basically not so much buffer. And again, it's because there's not so much to absorb the heat. Then in the next slide, what we have is the heat wave is over and the power outage is over. We have here again 1 week. And now we are trying to cool our building back to 26, 27, or 28 degrees. And then in here we can see, for example, the tabs lightweight and the other tabs conditions, they're able to, let's say, reduce the temperatures to where we wanted as very quickly. So in here, again, it's a similar structure of the graph. So in this case, now hours it takes for the building to get down to 26, 27, or 28 degrees. So in here, again, what we can see is that tabs is performing better. And in the sense that for tabs, it takes between 1 to 2 days for the temperatures to get back to 26 to 28 degree range. While for the convective system, it takes between 2 to 5 days. So we can see again the benefit of the tabs. And then even though the tabs is operating intermittently, here we can see if we wanted to get it down to 27 or 28 degrees, it can do that quite quickly, just like the other operation. but it would take longer for it to reach to 26 degrees because, again, we are doing the cooling intermittently. So I'll just very briefly talk about the PECS as well. So as I mentioned, one of the main benefits of PECS is that it can allow extending these temperature ranges. So basically, assuming the previous results, what we looked at is that, okay, if we assume that people had, let's say, a personalized environmental control system, it could be a dedicated PECS, or it could be, for example, something maybe as simple as a fan or desk fan under occupant control. We can see, or our assumption is that we can still provide comfort to people at temperatures above 26, 27 degrees, and then in here we have it until 30 degrees. Then basically what we can see here is that then the PECS allows us to, again, use the building for a longer period of time. You can see it can go up from 16 hours to 64 hours. And also the similar behaviors on once the heat wave and the power heat wave is over and the power is back. It can allow us to occupy the building faster, as for example, after we can get back to the building maybe after 64 hours instead of 120 hours almost. So a very quick example of how they could how these systems can help. So I'll summarize here what we have. So basically, radiant cooling systems and PECS, they have several benefits compared to more conventional systems of, for example, convective or air conditioning systems. And we also saw that they could be promising solutions during heat waves and power outages. So they have the resiliency potential. But obviously, we need different operation strategies, and their exact benefits will depend on several factors, such as the building type, building use, operation, and where they are in the world. So the future steps that we have is that we will obviously continue these simulations in a systematic way to quantify their exact benefits under different boundary conditions. Together with this work, we're working on developing quantitative key performance indicators, both for long-term, meaning, for example, a cooling season, or short-term, meaning maybe a matter of 3-4 days or a week. Based on all these, we want to develop design, sizing, and operation guidelines for these two systems that we talked about. And then one of the things we will particularly be looking at is the system sizing issues. If we should size these systems based on future weather files, or if yes, what would be a proper way to do it. And of course, most importantly, buildings and everything is buildings, or our built environment is for people. So of course, here we talk about what the building can do, what the system can do, but what we have to consider is what the people can do or what they can tolerate. So we'll develop an approach that can integrate what people can cope with into all these simulations and calculations. And with that, I will conclude my presentation, and sorry for running over time a bit. It's just a very interesting topic. Thank you for listening.